Why would a heavy electronic warfare aircraft, one designed from the outset to emphasize close-in suppression and long proven to have ample hardpoints, suddenly abandon some of its underwing hardpoints, and instead utilize the centerline underbelly position, which had previously been almost never used, to carry a brand new, rather sizable electronic warfare pod? What kind of replanning of the mission profile lies behind this, and what new thinking does it reveal regarding the tactical application of electronic warfare by this Air Force? Photos circulating online over the past 2 days have once again brought the J-16D, a twin-seat, twin-engine heavy electronic warfare aircraft, into the spotlight. The photos show the aircraft carrying a large pod, previously unseen in public, mounted on its central fuselage line. While carrying electronic pods on missions is routine for an electronic warfare aircraft, what makes this instance unique is the change in mounting location and pod model. This is far more than a simple adjustment to the mounting scheme. It points to a profound expansion of operational doctrine and mission profiles. To understand the significance of this change, we must first examine the global landscape of tactical electronic warfare aircraft. Currently, electronic warfare aircraft worldwide fall into two main categories: high-altitude strategic-level electronic warfare aircraft, which are modified from large transport or passenger aircraft, and tactical-level electronic warfare aircraft, which are modified from fighter aircraft and capable of penetrating enemy defenses alongside strike formations. The U.S. Navy's EA-18G has long been the benchmark in this field. Modified from the F-18E F airframe, it can carry 3 large electronic jamming pods under its wings and along its centerline in standard configuration, in addition to 2 fixed receiver pods on the wingtips. However, the EA-18G has one unavoidable shortcoming: the platform's inherent size limitations. Due to the Super Hornet's medium-sized airframe, its internal fuel capacity is relatively limited. For long-range operations, it typically requires 2 large external fuel tanks mounted under the wings to ensure sufficient range. Consequently, the heavy load hardpoints that could otherwise be used for jamming pods are occupied, forcing a constant trade-off between combat radius and jamming power. Even during short-range missions without external fuel tanks, its power supply capacity is constrained by the inherent power output of the engines and power generation system, making it difficult to simultaneously drive multiple high-power jamming pods to operate continuously across the full frequency spectrum. In contrast, the J-16D possesses inherent advantages at the platform level. As a variant developed from the Su-2730's heavy fighter, the J-16D is significantly larger than the EA-18G. With a maximum takeoff weight of 33 to 36 tons, it not only carries an extremely large internal fuel capacity, enabling a range exceeding 3,000 kilometers and a combat radius of over 1,500 kilometers, but, more importantly, the power supply and heat dissipation capabilities of a heavy platform are unmatched by medium-sized aircraft. 2 high-thrust turbofan engines provide ample electrical power redundancy, while the larger internal airframe space allows for the installation of a more efficient liquid cooling system, ensuring that the power amplifiers in the electronic pods can maintain high power output for extended periods. In past public appearances, whether at the September 2025 military parade or previous air shows, the J-16D has consistently demonstrated a standard configuration, featuring a fixed reconnaissance pod on the wingtip and 4 large electronic jamming pods under the wings. This setup delivers formidable electronic warfare capabilities and sufficient range without the need for any external fuel tanks. This configuration alone clearly demonstrates that the platform was designed with ample power and structural redundancy from the outset. So, if the original configuration was already so powerful, why switch to a belly-mounted configuration now? The key lies in the increased mission flexibility resulting from the reconfiguration of the mounting points. With the J-16D now carrying this new pod on its central belly mount, the heavy load pylons beneath the left and right intakes, previously used for large jamming pods, have been freed up. On J-16 series fighters, these 2 hardpoints are typically used to carry heavy ground attack munitions or large anti-radiation missiles. This means that the J-16D is no longer merely an electronic support aircraft, but rather an electronic attack aircraft that integrates electronic suppression with hard kill capabilities. In this new configuration, the fighter jet can perform 3 tasks simultaneously. The wingtip pods are responsible for long-range radiation source localization and signals intelligence collection. The positions under the wings that previously carried jamming pods can now mount anti-radiation missiles to execute hard kill missions, directly destroying enemy radiation sources. And the large pod newly mounted on the center line of the fuselage, judging by its dimensions and mounting position, is presumed to possess more powerful full-band noise jamming or deception jamming capabilities. This shift in mission profile holds significant tactical value. In traditional configurations, electronic jamming aircraft and anti-radiation strike aircraft are typically deployed separately. However, when a single aircraft possesses both capabilities, the response time from target detection to destruction is drastically reduced, and the complexity of operational coordination is consequently lowered. More importantly, when enemy radar operators detect jamming, they typically take evasive measures such as shutting down or switching frequencies. If a fighter equipped with anti-radiation strike capabilities is already in firing position at that moment, it can lock onto and attack the target within a very short time, after the radar is restarted or the frequency is switched. This continuous suppression effect is difficult to achieve with a multi-platform configuration. This adjustment in the configuration of the loadout also highlights the significant advantage of heavy fighter platforms in terms of tactical flexibility. For a fighter with sufficient size, there is considerable room for adjustment regarding how to utilize hardpoints, balance the center of gravity, allocate power, and manage cooling resources. The design team can flexibly switch between all software suppression and combined software-hardware modes based on mission requirements without needing to make any structural modifications to the aircraft itself. For medium-sized fighter platforms, however, such operations are essentially impossible. Take Europe's Rafale or Typhoon fighters as examples. If converted into electronic warfare variants, their limited internal fuel capacity would force them to prioritize the installation of external fuel tanks, leaving them stretched thin when mounting large electronic pods. Even the U.S. next-generation jammer project currently under development is constrained by the EA-18G's power supply capacity, forcing it to adopt a segmented frequency coverage design, a divergence in technical approaches stemming from differences in platform capabilities. Furthermore, this configuration reflects a precise assessment of the battlefield threat environment. When facing adversaries with strong electronic protection capabilities, the suppression effect of 4 pods is indeed superior, enabling a higher jamming power density. However, against most conventional adversaries, the power output of 3 pods is sufficient to achieve control of the electromagnetic spectrum. The tactical benefit gained by using the mounting point occupied by the extra pod to carry anti-radiation missiles is significantly higher. This flexible configuration allows combat commanders to select the most appropriate loadout, based on intelligence assessments for targets of varying threat levels. From a broader systemic perspective, the J-16D's recent configuration changes are also in step with the overall development of this Air Force's electronic warfare capabilities. As early as 2021, the J-16D and J-20 were deployed for combat-oriented training, forming the classic combination of stealth fighters taking the lead and electronic warfare aircraft providing accompanying suppression. In the field of carrier-based aviation, the J-15D, which shares the same lineage as the J-16D, is also scheduled for mass deployment and combat readiness by 2025. The J-15D similarly inherits the advantages of a heavy-duty platform, and the breakthroughs in both hardware and software achieved by the J-16D will provide significant technological benefits for the J-15D as well. The simultaneous deployment of these two heavy electronic warfare aircraft by both the Air Force and the Navy signifies that tactical electronic warfare capabilities have evolved from a supplementary force into a core component of the main combat system. The J-16D's recent deployment of a large pod, mounted on the centerline of its fuselage, is not merely a simple mounting test. It marks a new level of mission versatility for heavy electronic warfare aircraft. When electronic warfare platforms possess sufficient capacity and redundancy, mission planners no longer need to make an either-or choice between electronic jamming and firepower strikes. In potential future high-intensity conflicts, aircraft like the J-16D will be fully capable of both conducting electromagnetic suppression and directly destroying enemy radiation sources in a single sortie. This capability represents a new dimension that heavy platforms bring to electronic warfare,